Fermilab it's a facility. It's a laboratory with a very special facility used by scientists from many of the universities in the United States and by scientists from all over the world. Now, the facility is a particle accelerator.
Okay.
A large particle accelerator. If you look out, you'll see a ring of mound of Earth, which goes around 4 miles, I think. In the metric system, it has a radius of exactly 1 kilometer, and 30 feet below ground there's a tunnel. The tunnel is about 8 or 9 feet across, and in that tunnel are magnets. There's 4 miles of magnets, powerful magnets. The magnets function as part of a system called a particle accelerator. The best way to describe a particle accelerator is to say it's a very sophisticated form of a microscope. Microscopes are generally thought to be used in biology to clarify the structure of small microorganisms. And they enlarge the microorganisms. In the classical case, the scientist peers into his microscope and he sees this bug and he says, gee whiz, and he may make sketches of the bug. Today, the microscope is, even for the biologist, more sophisticated. He may have a camera on it. He may have an automatic camera. He may take lots of photographs. The photographs would be developed much later and analyzed in great detail. And probably in the most sophisticated microscopes, he might even digitize the information, put it into a computer, and write magnetic tapes, which you would analyze later on a computer. The more detail you want to see, the more powerful the microscope, the more complicated it is, the bigger it is in physical size. So if I want to see the hair of my head, I can use a rather low-power microscope, maybe even a magnifying glass. If I want to see a small microorganism which is crawling around on the roots, then I need a much more powerful microscope. If I'm interested in the tiny structures in this microorganism, the microscope has to be more powerful. And if I now generalize my research to looking at atoms, molecules, let's say, which is the next stage, we know that most of organic matter is composed of very complicated molecules. Then I need an even more powerful microscope. And we're getting towards the kind of thing which is also called an accelerator of particles. So philosophically, an accelerator probes down into the inner structure of matter, through the molecules to the atoms, and then the core of the atom is the nucleus. And then one zooms down, if you like, by building more powerful accelerators. And at each stage, the accelerator is bigger, covers more territory, evolves from a desktop thing to the kind of real estate hungry object that you see outside the windows at Fermilab. At the stage we're in here, we've gone long past the molecules, long past the atoms, long past the nuclei, long past the neutrons and protons, which are the constituents of the nuclei, and we're trying to find the inner structure of the neutrons and protons. So, to review Fermilab's reason for being is that the creation of this kind of an accelerator takes an enormous effort. It's obviously very expensive. It takes the talents of literally thousands of people to put this together, combinations of scientists and engineers and technicians, workers generally. And therefore there are not many of these laboratories around the world, and so people travel here from all over, bringing apparatus in order to answer their particular quest for the structure of matter. So Fermilab is that kind of a physical laboratory.
At Fermilab, people are studying the fundamental structure of matter, what matter is made out of, the atoms, the subatomic structure, quarks, leptons, the very basic building blocks of all of matter, going inside the atom, inside the atomic nucleus to find these basic building blocks. One of the major goals of astrophysics, particularly cosmology, which is the study of the universe as a whole, is to figure out where it came from, what started it, how was it created. Well, we know that the universe is a Big Bang universe. It's at one time that was very hot and dense and has expanded to the present universe that we have today. As we extrapolate back to that hot and dense time, we know that the particles, all the matter in the universe, was moving about with higher and higher energy. Well, that's exactly the kind of conditions that one is duplicating in an accelerator. So in some sense, an accelerator that's accelerating particles to high energies to do collisions, to explore the nature of matter, is also duplicating the conditions of the early universe. So there's this natural tie together between the early universe, where you're having to worry about what were things like when everything was moving around at high energies, and what you do in an accelerator. But even more so, in the past few years, this connection has grown, and the fact that what we've learned in the early universe as we go back to earlier and earlier times is that we have questions that we did not know answers to. And the new developments in elementary particle physics are giving us answers to some of those questions.
Why do we talk to astronomers? Because the astronomers understand that in the Big Bang, the temperatures were so high that matter had to be reduced to its most primordial fundamental components. And they said, well, who knows about this? All those physicists with their microscopes, they know about the primordial fundamental components. I hear they talk about quarks. So they come and visit us and we discuss. And we find we have to know about the quarks. We have to know about the forces between quarks. We have to know everything there is to know about these objects, because in the beginning of the universe, they were dominant. Today, the quarks themselves, you can ignore them and understand all about chemistry and biology and so on, and computer science and most of technological civilization without really being aware of quarks. But in the earliest moments of the universe, they and any more fundamental objects dominated the universe. And so our experiments are totally crucial to an understanding of how the universe evolved. And you get some feedback the other way, because the universe did evolve. It did come to where we are today, and that gives us some constraints on our own theories. They can't be too wild, or when the astronomers pick up a wild theory of particles, it turns out to be inconsistent with the evolution as observed. So there's a back and forth communication.
Cosmology underwent another very important and very exciting transition about 6 years ago by receiving some new information which came out of particle physics. Let me go back now and talk about particle physics. That's really the field that I come from. During the period of the late 60s and the early 70s, particle physics underwent a very exciting time in which many very fundamental problems were solved. And by 1973 or so, we had a theory, which we now call the Standard Model, which seemed to correctly explain absolutely all particle physics data that existed in the world at that time. Now, we still weren't sure that this theory was right. Some aspects of it were not well tested, but it looked very good. In this atmosphere of success, people tried to extrapolate the model further to build a theory which would actually predict the behavior of matter at energies which were far greater than had ever been obtained. And out of this drive came a class of theories called grand unified theories, the first of which was discovered by Georgi and Glasgow in 1974. Now, these theories make predictions for the behavior of matter at temperatures which were previously considered totally extraordinary. Now, once you can understand the behavior of matter at higher and higher temperatures, it means that you can push back your understanding of the history of the universe to earlier and earlier times. And that has been the role which particle physics has played in the development of cosmology.
In the history of science, and especially of the modern period, scientists have been driven to build more powerful facilities, microscopes for the subnuclear domain, in order to answer outstanding puzzles. Notoriously, the new facilities have yielded more than answers. They have exposed new phenomena and generated new puzzles. Although we have many burning questions on our agenda, we cannot predict the scientific impact of the Tevatron program based upon the superconducting energy saver. If history is any guide, the fruits of the efforts of so many, the designers and builders, of the statesmen in the U.S. Congress and in the Department of Energy, and ultimately the paying public, will be to return to society something profound to enhance our culture and perhaps even the quality of our life.